All right, welcome. This is reviewing everything you need to know about limits in 20 minutes. Let's say a function f gets really very close to a single value L. As it approaches a value c in the x-axis from the left and the right. This is how we denote it. The limit as x goes to c of the function f gets really close to L. Let's take a look at this example real quick. We have the function f of x equals x squared. And I'm trying to show that the limit as x approaches 1 in the x-axis, then f of x will get really close to 1 in the y-axis. So let's take a look what's happening. As x approaches 1 in the x-axis, we start to see in red that y begins to approach 1 in the y-axis. We also have this notion of a one-sided limit. Limits don't need to come in from both sides. We denote a left-sided limit coming in from the left side with a negative sign. And we denote a right-sided limit coming in from the right side with a positive above the c. This one is only analyzed coming in from the right, and this one is only analyzed coming in from the left. Alright, let's go ahead and do these one-sided limits real quick. If we take a look at the first one, it's asking us to go to -1 from the left-handed side. So what we're going to do is only come in from the left side and see where we get really close to -1. We're coming in here and we actually get really close to 4. And as we do it from the other side, we're taking a look only from the right side, given the plus sign above the -1, and we're approaching -1. We're getting really close to -1 from the right-hand side, and it ends up getting really close to 2. All right, now we're going to try and solve this limit, but we're not doing one-sided limits now. There's no plus sign or minus sign above the -1. We are just trying to find the limit as x approaches -1. So we approach from the left-hand side and the right-hand side and see what we get really close to. The problem is this. As we get really close on the left-hand side, it gets really close to 4. While if we approach -1 from the right side, we get really close to 2. Because of this, if the left and right-hand side do not meet, we say does not exist. So the left-hand sided limit and the right-hand sided limit must be equal to each other if we want the limit as x goes to c to exist. If these do not exist, then what we're going to get is that this does not exist. Alright, these are some of the algebraic limit properties of limits. If a is a real number, then plugging in a limit as it goes to a is just going to stay going to a. If a is being multiplied to f of x and f of x goes to L, then we can just multiply a by the limit of L. And instead of having to do a limit of two functions together, we can do the limits individually and then add them up after. Similar, we can do the same thing for subtraction. If two functions are being multiplied, we can take the limits individually and then just multiply the limits. Lastly, we can also do division of the limits individually and then divide the limits after. Granted, m cannot equal 0. Alright, so we're given the limit as x goes to 3 of f of x equals 2. Similarly, we're given that as x goes to 3 of g of x, we get 4. So now we need to find the following. Well, we know that 4 is just a constant number. So as x goes to 3, it's just still going to give us 4. With this one, what we can do is we can actually just split it up so that we're only doing 4 times our limiting value, 2. That'll give us 8. For this last one, we can just plug in our limit values into it using the algebraic limit laws that we know. we know that this will be 2 divided by 4 plus 2. This is going to give us 2 1/2. Another technique for solving limits is using a numerical approximation, using a table. Given an x value, we can get our x value really close to 1, which is in this case where we're trying to analyze our limit at. And we just are trying to observe what numbers does x squared minus 1, our function, what numbers does it get really close to as we approach 1 from the left and the right. Okay, we see that this number is getting really close to negative 0.002. This one's getting really close to 0.002. It appears that our limit is getting really close to 0. Therefore, we can approximate our limit as x goes to 1 of x squared minus 1 to equal 0. One way we can do limits is through direct substitution, in which we just take our value that we're approaching in the x-axis and just try and directly substitute and see what happens. So for this one right here, we can try and directly substitute the square root of 4, and our limit actually approaches 2. In this limit right here, as x approaches 3 of x squared, we can plug in 3 squared. That'll give us 9. That's the answer to our limit here. And our last one, we can directly substitute 2 in for 2x plus 3. And we'll find that the limit is going to equal 7. Of a limit, we might get this indeterminate form, meaning that we don't know yet if the limit exists or not just by plugging in the number x goes to 2. If we take a look at this one, we'll see that we'll get 2 squared minus 4 over 2 minus 2. Well, this right here is going to be 4 minus 4. That's going to give us 0 in the numerator. And this 2 minus 2 is going to give us 0 in the denominator. Thus, this gives us one of our indeterminate forms. The thing that we can do to solve this limit is by factoring out. And in this case, x squared minus 4 is a difference of squares. So if we change it into x plus 2, x minus 2, we might get better success with this limit. Alright, now that we factored x plus 2, x minus 2, which was the difference of squares we originally had, we can cross out this x minus 2, x minus 2. Thus, we're left with only an x plus 2. Now we can go ahead and solve this limit. This is going to give us a direct substitution, 2 plus 2, and our limit is actually going to go to 4. And geometrically, this is what the graph of x squared minus 4 over x minus 2 looks like. And if you take a look, as we get really close to 2, we see that from the left and the right, although it's undefined at the point, our limit does get really, really close to 4. Therefore, the limit as x goes to 2 of this function does approach 4. Another way we can solve these limits that would give us an indeterminate form if we substituted is by multiplying by the conjugate. Now, if you do direct substitution, you'll see that you're going to get 3 times 3 minus 3 all over 3 minus 3. This is going to give us 0 over 0. So instead, what we can do is multiply by the conjugate, a different form of 1. If we multiply by 3x plus 3 over 3x plus 3, what we'll see is that we will end up getting 3x minus 9 over x minus 3 square root of 3x plus 3. We can factor this even more by pulling out a 3, and we'll get x minus 3 on the top. Therefore, we can now cancel out this value right here and this value right here and analyze the limit. All right, now we can use direct substitution. We are going to get 3 on the top, 3 times 3 on the bottom plus 3. This is going to give us 3 over 6. Or 1/2. Is limits that we take to infinity. We also call this sometimes the end behavior. We're trying to see what happens to a graph as we get so far to the ends of the earth that it either hones in on a single value or is unbounded and goes up to infinity or down to infinity. So for this limit, we see that x goes to infinity, and this is the function x squared. Well, if we look as we go to infinity, this value is just going to continue going up, 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 never stopping without bound. So this limit is going to equal infinity. Another limit to infinity is 1 over x. Again, we're trying to see what happens as we push towards the ends of the earth of this graph. What is happening to 1 over x? Well, we see it gets really, really, really small really fast, and it continues to decrease and get smaller and smaller and smaller. It's as if it almost gets to 0. Therefore, the limit as x goes to infinity of 1 over x equals 0. Another way to think about this to show that our limit as x goes to infinity of 1 over x equals 0 is by using a numerical table and seeing what happens as we plug in x's that are larger than the last. Alright, so I have some x values that I want to plug in to our function, 1 over x, and we see that if x equals 1, then 1 over x equals 1 over 1. Now if I plug in 10, we're going to get that 1 over x is 1/10. This is definitely smaller than 1 over 1. If I plug in 100, we're going to get 1 over 100. And then 1,000 is going to give us 1 over 1,000. And then 1,000,000 is going to give us 1 over 1,000,000. What this is saying is that as we plug in x values larger and larger, getting closer and closer to infinity, we get values in 1 over x that are getting smaller and smaller, closer and closer to 0. So whenever we try and do the limit as x goes to infinity of a rational function, what we do is we actually look at the dominant terms. In this case, the dominant x term is an x squared in the top. And in the bottom, we have an x. Because we're going to infinity, these numbers are getting so large that this 3 and this -5, they're going to be negligible. We don't even need to analyze them to figure out what happens as x goes to infinity. Okay, so what we're essentially doing is we only need to look at the dominant terms in the top and the bottom, the numerator and the denominator, to figure out what's actually happening in this rational function. Well, in this case, we have 2 x's on the top and 1 x on the bottom, so we can cancel out 1, and it's essentially like what's happening as the limit as x goes to infinity of x. Well, this is just going to keep going to infinity, so our answer is infinity. Similarly, if the dominant term is x on the top and x squared on the bottom, because the dominant term overpowers in the bottom, keep in mind that this 3 and this -5 will be negligible as x goes to infinity. It's almost as if we have x over x squared because the 3 and the 5 are negligible. So in this case, we're going to have x over x times x. We can cancel out an x in the top and the bottom, giving us 1 over x. Using the same logic like we did before, the limit as x goes to infinity of 1 over x, that's going to give us 0. So our original limit, because the dominant term is in the bottom, this will also equal 0. So take a look at this limit as x goes to infinity of the function sine of x. Well, sine of x continues to oscillate up to 1, and then it goes down to -1, and then it repeats again. It goes back up to 1, and then it goes down to -1, and then up to 1, and it keeps doing this oscillating motion forever and ever and ever. So as we approach infinity, what's going to happen is we're going to keep moving from 1 to -1, 1 to -1. Therefore, it does not hone in on a single value, and sine of x, the limit as x goes to infinity of sine of x, does not exist. Here are two very important limits that we see in calculus a lot. Now, if I were to plug in for this first limit, direct substitution, sine of 0 over 0, well, on our unit circle, at 0, sine of 0 equals 0. The problem is that sine of 0 over 0, when we directly substitute, is going to give us 0 over 0, or that indeterminate form. Instead, sine of x over x as x gets closer to 0 is equal to 1. And if you were to directly substitute 1 minus cosine x over x with x equal to 0, what we're going to see is 1 minus cosine of 0 over 0. This will also give us 0 over 0. Instead, this limit as x goes to 0 is actually going to equal 0. These are two important limits that you should memorize. Another technique for solving limits is called squeeze theorem. Let's say we have three functions, f, g, and h, and f is smaller than g, and g is smaller than h. But if we know that the limit of f and the limit of h both go to the same value, well, because this is equal to L and this is equal to L as they approach C, it must follow that the middle function, g, must also go to L. All right, let's solve this using the squeeze theorem. So we know sine of x oscillates between -1 and 1. Therefore, the value of sine of x will always stay in between -1 and 1. Now, if we divide all three of these by the value x, what we're going to get is that sine of x over x is going to be in between -1 over x and 1 over x. All right, and now we take the limit of all three of them. Keep in mind that this is our f of x, this is our g of x, and this is our h of x, like we were given in the definition. If we can show that the f of x and the h of x equal the same limiting value, then the g of x must follow. Well, we know that the limit as x goes to infinity of -1 over x, as it gets closer and closer to infinity, this value, -1 over x, is going to get smaller and smaller and smaller as we plug in larger x's. So this is going to go to 0. Likewise with 1 over x, as we plug in x values getting closer and closer to infinity, 1 over x will keep getting smaller and smaller and closer to 0. All right, now we sub in what we know about the limit of -1 over x and 1 over x as they approach infinity. What we're going to get is 0 is less than or equal to the limit as x goes to infinity of sine of x over x, which is less than or equal to 0. This means that the answer to the limit as x goes to infinity of sine of x over x, this must also equal 0.